Hello physics students, here is an exam 3 review on the topics of linear momentum, rotational motion, angular momentum and static equilibrium. Momentum is the product of mass and velocity. Impulse can be calculated in two ways, either as the product of force and time or as the change in momentum. Here are the important equations that we have gone over several times. Remember that momentum is conserved when there is no external force acting on the system. So the total momentum will be constant. And this is true both along the x and the y axis. Now this is a question on the application of linear momentum. You're coasting on a 10 kilogram bicycle at 15 meters per second and a 5-gram bug splatters on your helmet. The bug was initially moving at 2 meters per second in the same direction as you. If your mass is 60 kilograms, what is the initial momentum of you plus your bicycle? What is the initial momentum of the bug? What is your change in velocity? And what would be the change in velocity if the bug were traveling in the opposite direction? Now, momentum is just the product of mass and velocity. So in the first case, got to add the masses of both the bicycle and the person. Just 70 kilograms times 15 is 1050 kilogram meter per second, which is 1.1 times 10 to the 3 kilogram meter per second. The initial momentum of the bug, likewise, you got to change the gram into kilogram and multiply with the velocity of the bug. When you do that, you get 0.010 kilogram meter per second. Now for the C part, you have to apply the principle of conservation of momentum, which is the momentum, total momentum before collision is equal to the total momentum after collision. If you have the momenta before collision, that's equal to the sum of the masses, because the bug sticks to the helmet, times the velocity, which gives the velocity as 14.99907, and therefore the change is the final minus the initial, which is this number, 15 minus, so you get, actually it should have been the other way around. I wrote it, okay, I made a mistake there. It should be 14.99907 minus 15. That was what was in my mind, but when I wrote it the opposite. So that's why you get negative that small number. Now the D part, what would be the change in velocity if the bug were traveling in the opposite direction? Now if the bug were traveling in the opposite direction, the momentum would be negative instead of being positive. So you see that it's negative, the same number here. And that would give this velocity as the final. Therefore the change would be that number minus 15 actually, which will give you a negative 0.0012i. So it should be reversed, that number minus, and then that will give you negative. All right, here is another question. This is on center of mass. You have to find the center of mass of a 1 meter long rod made of 50 centimeters of iron and 50 centimeters of aluminum. And both of their densities are given. So here's the diagram. So you have the rod here, and this part is iron all the way up to here, and from here up to here is aluminum. And the center of mass of the iron would be exactly at the center, which is going to be 25 centimeters from one end. And the center of mass of aluminum is going to be again at its center, which will make it 75 centimeters from one end, right? So that's 75. So I've called them R1 and R2. R1 is 25 centimeters, R2 is 75. That is iron, that is aluminum. Now to find the center of mass, the position vector of the center of mass is M1R1 plus M2R2 by M1 plus M2, where M1 is the mass of iron, M2 is the mass of aluminum. And the two volumes here are going to be equal, and volume multiplied by density gives mass. So you see that the mass of iron is going to be at 8 times the volume, because 8 is the density, and I'm keeping it in gram per centimeter cube. It's okay. Times 25 plus 2.7 times volume times 75, okay, divided by the sum of the masses. And when you do the math, the volume is going to cancel out completely at the end. And therefore the center of mass is actually 37.61 centimeters from one end, while it is 12.6 centimeters from the center of the iron. I'm going to show that right now. So that is the point of center of mass, and this is 12.6 centimeters, and this is what we got as 37.61 centimeters. So that's how you do that problem. Which brings us to rotation. In this chapter there are some key terms like angular acceleration, which is the rate of change of angular velocity, and you have the parallel axis theorem. Parallel axis theorem, where if you know the rotational inertia about the center of gravity, then you can find the rotational inertia about any axis parallel to the axis passing through the center of gravity. Those are the key terms, and these are the formula here. You see that angular velocity is angular displacement by time. Linear velocity is radius times angular velocity. Angular acceleration is d omega by dt, which is also d squared theta by dt squared. And then a tangential acceleration is r times alpha. And then you have the rotational equations that are comparable to those in kinematics. So these are the important equations that you need to know. And let's see if we can do this problem. This question says the angular velocity of a rotating rigid body increases from 500 to 1500 revolutions per minute in 120 seconds. What is the angular acceleration of the body, and through what angle does it turn in this 120 seconds? First of all, what is given is revolutions per minute, which you got to change into revolutions per second. That gives you the frequency. And once you multiply the frequency with 2 pi, you get the angular velocity. Here we go, this is the initial frequency. Here is the final frequency, both in rotations per second. And if you multiply them with 2 pi, each one with 2 pi, you're going to get the angular velocity. Which will be in radians per second. And then to find the angular acceleration, find the change in angular velocity divided by time, which is what is given here, and substitute and calculate to get 0.87 radians per second squared. To find the angle, use this equation, omega it plus 1/2 alpha t squared. Plug in the numbers and calculate to get 12545.5 radians. So that is how you do these problems. This is just an example of working out one problem using those equations that are comparable to the equations in kinematics. This is an interesting question. You have a hanging mass attached to a string passing over a pulley, and there is another mass at the other end that is on an inclined plane of angle 30 degrees. The question is, what hanging mass must be placed on the cord to keep the pulley from rotating? So that means there should be no rotation, which means there should be no motion. So what is the minimum mass that you can keep here so that it doesn't move? And it says that the inner radius of the pulley is 20 and the outer radius is 30. Obviously this string passes over the inner radius while this one passes over the outer. And the weight of the object, this object acts vertically down. It can be resolved into the component that is parallel to the inclined plane, which is going to be mg sine theta. That force acting here is going to create a torque, which is mg sine theta times the radius. Okay, so it's mg and mg sine theta. The torque is going to be mg sine theta times the radius, which is the inner radius, which comes out to be, when you put in those numbers, 4.9 Newton meter. Now this torque must be exactly balanced by this hanging mass, which means this must be equal to m2g times 0.3, because the torque here is simply the weight of this multiplied by the outer radius, which is what's given there. So from there, m2 is calculated to be 1.67 kilogram. Very interesting application of torque. All right, which brings us to angular momentum. And this chapter, of course, has the conservation of angular momentum. Angular momentum is defined as the product of rotational inertia and angular velocity. There are other important equations in this chapter. Angular momentum is also, that is, by the way, that's L. It's the cross product of R and P. It's a cross product of the position vector and the linear momentum. Also, net torque is equal to dl by dt. All right, here it's given here. Net torque is equal to dl by dt. And conservation of angular momentum comes with the condition that there should be no net torque acting on a system, and in that case, angular momentum is conserved. Here is a question that gives the position vector, the velocity, and the force. You're asked to find the angular momentum. Angular momentum is R cross P. And P is the linear momentum, which is mass times velocity. So that is the radius or the position vector times mass, which is 1.0 kilogram, times the velocity. Velocity is in meter per second and the position vector is in meter. So rearrange this to take the mass on the outside and take the cross product of these two vectors, ijk, put the coefficients 2, -4. I missed the -4 there, but I'm going to correct it. -4, 6, -1, 4, 1. So when you go I, you go 4 times 1 minus 6 times 4, right? Which is 4 minus 24, minus j, 2 times 1, minus of minus 6. So that's why you have 2 plus 6, and k would be 2 times 4 plus 4. Okay, when you put the negative there, I got to change this also to negative. Okay, so that's what I'm doing now. So you get 8 minus 4. So you get this vector. That is going to be the angular momentum. Second question is, what is the torque? Torque is the cross product of R and F. So do the same thing, except that now you take the cross product between R and F, just like we did before. And when you do that, you get negative 90I plus 60J plus 70K. This also shows you how to take cross products. So that is an important problem. Here is a question, another one. A bug flying horizontally at 1 meter per second collides and sticks to the end of a uniform stick hanging vertically. So the bug comes and hits the stick, which is hanging vertically here about a pivot. And as soon as the bug hits it, you know, it makes the stick swing to a maximum angle of 5 degrees from the vertical before it rotates back. And the mass of the stick is 10 times that of the bug. Calculate the length of the stick. So here we again apply conservation of angular momentum. And angular momentum is mass times linear velocity times the distance, which is the length here. So this is the initial angular momentum of the bug. Because the bug is hitting at this point, you take the length as the radius, multiply with the mass of the bug times its velocity, which should be equal to the final. Finally you have the rotational inertias of the stick and the bug times omega. Now the stick has 10 times the mass of the bug, so 10m L squared by 3. Why? Because the rotational inertia of a stick is actually mass times its length squared by 3, right? About one end. plus that of the bug is just ml squared. So rearrange that to get omega. Which comes out to be 3v by 13 times the length. Now we can also use the energy concepts, because initially the bug has kinetic energy, but finally, both of them are raised up through a height h, so they have potential energy. So the initial kinetic energy of the bug is equal to the total potential energy of the bug and the stick. And when you try to find the height, you have to use this angle to find the height. And you can see that, all right, that is UF, okay. U stands for potential energy. So initially you have 1/2 the rotational energy of the bug plus the rotational energy of the stick, omega squared, swinging up becomes equal to the potential energy of the bug and the stick. Now this whole thing has come about because we're trying to represent h in terms of the length. So there is a little bit of trick there, which we have done during the lab. So I'm not trying to explain that there. So when you do those calculations, that is the, for the rotational inertias of the bug and the stick. That's for the bug, that's for the stick. And omega, which we had got before, has been substituted. And then you have the right hand side. Make the length the subject, because that is what is to be calculated. And the final answer comes out to be 0.52 meter. 0.52 meter. Which brings us to static equilibrium. And here, the main idea here is that for static equilibrium, two conditions have to be maintained. One, the net force must be 0. And 2, the net torque must be 0. Net force and net torque both have to be 0 for static equilibrium. This is an interesting question. You have the setup here, you have 4,000 newtons here, and then 2,000 newton here. And the question is, what force must be applied at this point P to keep the structure in equilibrium? If you look at this, you see that this creates a counterclockwise torque about the point P, and this one creates clockwise torque. And the clockwise torque is going to be 4,000 times 1. Counterclockwise is going to be 2,000 times 2, which is equal. And now there is no force that you can apply at P to keep it in equilibrium. So it's not possible, because any force at P will not create a torque, because that's the axis of rotation. And there is no distance from the axis of rotation. So it's not possible to apply any force at P in order to balance the arrangement. Which brings us to the last question in this review. You have a ladder here kept inclined, and it has a length of 6 meters, a mass of 10 kilograms. and there is a person of mass 70 kilogram standing 3 meters from the bottom. The center of mass of the ladder is 2 meters from the bottom. You got to find the normal reaction and friction forces on the ladder at its base. Alright, so before doing that, let's look at all the forces that act. That's 2 meter. That is the weight of the ladder acting through its center of mass, 10 kilograms. And that is the person's mass shown there. Now these are the three forces. This is the normal reaction here, friction, and this is the normal reaction at the wall. We've been asked to neglect the friction here. So this is the arrangement. Let me label them as N, F, and N prime. And from this arrangement, we know that the total upward force must be equal to the total downward force. Total up is N, or along the y-axis is N, and here it's 80. So N must be equal to 80 kilogram weight, which when multiplied by 9.8 gives 784 newtons. So that is done. Now when you look at the forces along the y-axis, there are only two forces. One is N prime and the other is friction. So they have to be equal to each other. And since both are unknown, in order to find it out, let's calculate the torques about this point, which means all distances have to be measured from here. And also these two forces have no torque there. So the torque due to this force here is going to be the force multiplied by the perpendicular distance, which is this. See that? This distance. Because you take the distance, perpendicular distance between the line of action of the force and the point. So this distance. And this distance can be found out from the right angle triangle here. Anyways, that creates the counterclockwise torque, while these two together create the clockwise torques. And they have to be equal. So we are calculating the torques about the ground end of the ladder. Alright, so that distance is 5.65 meter. Just by squaring this, subtracting the square of this and taking the square root. And then N prime times this should be equal to 10 times this distance is going to be proportionally 2/3 of 2, right? 2/3 of 2 or rather 1/3 of 2, I mean 1/3 of 2. Why? Because this is 1/3 of 6. It's 2 meters, so this should be 1/3 of 2. That's why I have multiplied with 2 by 3. And then since this is half of 6, this must be half of 2, which is 1. That's why I've multiplied with 1. So when you do that and calculate, you get N prime as 13.57 kilogram weight, which is 132.97 Newton. So friction is 132.97 Newton. I hope this review has been useful. Good luck on the exam. And let me know if you have any questions or comments. Thank you.